Hi, welcome to Triple Creek Radio Control Club. Today we're going to talk about helicopter electronics, specifically the gyros, the solid-state gyros that are inside the helicopter, and also address some of the complex electronics that make these helicopters fly. First I'll introduce myself. My name is Bob Scher. I'm a member of the TCRC Club, and been a member since about last October. Relatively a newbie, and I'm new at flying helicopters, and I'm very fascinated by how they work as well as how to actually fly them themselves. I'm interested in the electronics. My background is I'm a retired electronics engineer. I worked in development and design of many small electronic projects and silicon development, and I find these solid-state gyros very fascinating. So first we'll talk about the helicopter a little bit and what makes it fly. Right here we have the main rotor blades. Obviously we have these blades start spinning around, and these blades will spin in a clockwise fashion, kind of like that direction. The pitch on the blades is going to cause a thrust, making the helicopter raise by blowing air down. That's the obvious part. There's some parts of this that are not intuitive at all, and there's some very strange forces that have to be overcome to be able to fly such a helicopter. First thing I want to discuss, I'm going to turn my transmitter on. I'm now going to turn on my electronics pack, and this pack is going to operate the swash. If you've seen that go up and down. The electronics pack is now powered. It's powering the servo motors that operate the condition of the swash. It is activating my 3-axis solid-state gyro. It's also activating the receiver that's receiving the spread spectrum signals at 2.4 gigahertz from the transmitter. What is not powered at this time, for safety reasons, down here is the battery pack, which is a large LiPo pack that runs the motor off of this electronic speed control. That is not powered at this time, and there's no need for us to power it for the demonstration we're going to be doing. When this pack does get powered, you have to exercise extreme caution that this blade doesn't come around and hit you or anybody else in the vicinity. So for now, we just leave it disconnected. One of the things that I've noticed right off when I got this helicopter put together is trying to understand how it operates in space, why it flies the way it does. And let's talk about a particular motion. Let's say we want this helicopter to pitch forward. Well, intuitively, you'd think we want more lift on the back blade versus less lift on the front blade. The back blade would lift up, the helicopter would pitch. That seems fairly obvious. But let's watch what happens. If I operate what would be my right stick and pull down on the elevator, you might notice that that blade is barely moving at all. There's really no pitch change on the blade whatsoever. However, if I would attempt to make it roll from left to right, notice the pitch is changing? Well, let's question that. Remember, I want this helicopter to pitch forward. To make it pitch forward, I'm going to push the nose down, but yet the blade isn't moving. That's kind of strange. So let's focus in on that particular issue and see if we can make some sense out of it. Okay, so what we just showed, I just powered down the helicopter, and we just discussed the fact that if we want this thing to pitch, we noticed that there was no movement of the blade in this position. Actually, the blade would have to be in the sideways position when we pitch up and down, and that's not intuitive. Why would the blades in this position pitching cause the nose of the helicopter to go down rather than in this position? So let's discuss a physical property called precession. I have this little prop here, just a pie plate and a spoon, and this represents a bicycle wheel. We all rode a two-wheel bike and learned how to balance on two wheels. If you remember, as a kid learning how to ride a two-wheel bicycle, in order to keep it balanced, we kind of steered back and forth, and somehow that helped us balance the bike. And as we learned how to ride the two-wheel bicycle, we kind of made less obvious movements of the steering wheel, and now that we can ride a two-wheel bike, we don't even pay attention to the fact that we are balancing by steering the bike. And what that's all about, as the bicycle wheel is turning, what we do in physics to meter the angular momentum of a spinning wheel is we take our right hand, and we call it the right hand screw rule, because if we want to put a screw into this board, we would turn it in the direction of our fingers, righty-tighty, lefty-loosey. So with the righty-tighty, we're going to use the same rule. As this thing is spinning in this direction, looking at it this way, it's clockwise. We take our fingers, wrap them in a clockwise manner, and notice the thumb is pointing out. That thumb represents the spin angular momentum. And the more this spins, the heavier it is, the larger the spoke diameter, the larger this, we call it a vector, the force, representing the spin angular momentum of this spinning plate. If we take this wheel, what makes this very interesting, if we take this wheel and turn to the left, what we're doing in essence is taking this spinning momentum and we're going to rotate it towards the left. We're going to torque it. As we torque it, again, we take our right hand, wrap it in the direction of the torque, and we notice now we have another force going up. This force here is the torque force. And what we learn in physics is that the spin angular momentum, the force going to the left, chases the torque, which in this case is pointing up. And what we wind up with, as this force chases this force, it rotates towards the right. So with our bicycle, if we turn our wheel to the left, the whole wheel, the whole bicycle, will tilt over towards the right. And that's called a precession. And the same thing is happening here. What we have here is spinning around in a clockwise direction. We have spin angular momentum. As we create a torque, again, the torque is rolling the helicopter forward. The torque is going in this direction. The spin angular momentum is going down. The torque is going this way. So the torque is going to follow the spin, is going to chase the spin, and the helicopter is literally going to roll this way. So if we were to lift the back with pitch, the helicopter would actually roll to the side. And it turns out that conversely, if we lifted this side with more lift, the helicopter would pitch. So what we have is almost a reverse effect where the helicopter lift is operating 90 degrees ahead of where we want it to be. And that's due to precession, and we have to make up for that in our flight controls. Okay, so we talked about the angular momentum caused by the spinning blades. The more mass we have out here, the more stable a helicopter will be. Traditionally, what they did is they put mechanical fly bars that would give the helicopter more stability. This mass would probably be 2 feet in diameter, and it's fairly clumsy, has a lot of little linkages and such to make it work, requires some complex tuning of it to get it balanced properly. And in today's world, what we're going to do here is miniaturize this big mechanical fly bar into a microchip that's in this 3-axis controller that's probably the size that would fit on the head of a pin. So we're going to talk about how that could be done. As we talked about here, what we had here was the mechanical wheel turning around. We're going to talk about some other physical properties, and I have little props here to discuss that. This bent wire here represents a tuning fork, the same type of tuning fork that you'd use to tune your piano, tune a guitar string, or any other musical instrument. What they actually do is implement a tuning fork in silicon, and it too would be about the size of a head of a pin. And the physical property of the tuning fork, if we were to bang this tuning fork, it would start oscillating in a pattern, in and out, let's say, like this, in this plane, in a plane like this, in and out. And the frequency that it would go in and out would be somewhat dependent on the length of these tines, the weight of the material. Perhaps it's definitely not how hard you hit it. This thing has a natural resonance of vibration. The interesting physical property of a tuning fork is if you rotate this fork, giving it angular acceleration, will actually start vibrating in another plane rather than just in and out as the initial force gave it. It actually start rotating in this plane here, let's say going forward and aft, as well as its initial excitation going in and out. And the more angular acceleration you give it, the more the force will be transferred to the in and out relative to the initial excitation. And that's all based on what we call the theory of keeping the conservation of angular momentum. You can't create or destroy angular momentum. The system has a certain amount of momentum, and as we add momentum by twisting it, we actually are creating forces in other directions to cancel that so that the net result change is zero. A more prevalent type of gyro is what we call a ring gyro. And this is typically what's in here. This is a little prop I'm going to use to explain how a ring gyro works. The interesting thing is, it's almost incredible. This year, 2012, there's probably a $2 billion market in ring gyros. $2 billion worth of ring gyros are sold this year. Where are all these ring gyros going? They're obviously not just going into model helicopters. These ring gyros are being used in automotive sensing systems. Your car most likely has an automatic braking system, anti-skidding system, traction control system, airbag deployment system, collision avoidance system. All of these motions that your car may take by skidding and as you twist your steering wheel to correct for a skid, all of that is being metered in these little angular acceleration sensors, typically using ring gyros. Cell phones, surely you've noticed in your cell phone, if you take your cell phone and rotate it 90 degrees, all of a sudden the display will follow your rotation. iPads, personal notepads, they all have this angular detection system, typically done with ring sensors like we're going to describe. So how does that work? This is just a plastic ring that we cut out of a bottle. I have two squares here, a pair of red and a pair of green, just to show what we're going to do. These red ones we're going to call our deflection excitation sensors. And what we do in electronics, we're going to repel and attract this red sensor to a plate. And by pulling this in and out, we create an elliptical shape, and we excite these electrodes such that this thing is vibrating at a certain resonant frequency. And it turns out that if this system, while it's vibrating, is rotated, if this helicopter rotates, or your car rotates, or your cell phone rotates, this vibration will be transferred into a 45-degree axis from the excitation. Now, if you remember the tuning fork, that had an excitation that rotated 90 degrees away from where it initially excited. In this case, we rotate 45 degrees. So inside of this 3-axis gyro is actually 3 of these little rings in different planes to measure pitch, up and down, roll left and right, and your rotation. So again, we just have this little ring gyro, and again, this ring gyro has been miniaturized down to fit on the head of a pin. I find that fairly incredible that we can meter things in such microelectronics. One of the aspects of our club that makes it so much fun is it's almost like a fraternity. There's different groups of people within the club that fly planes, helicopters, and different types of RC equipment. And the group I kind of hang out with are the helicopter guys. They taught me a lot. If it wasn't for their support, I would never have been able to put this together and learn how to fly within the period of time I have. And like I mentioned, I've been doing this about 9 months. One of the fun things of belonging to such a group, we buy our parts from different distributors. There are some major distributors online that support all of these kits and parts that are required to keep them going. One such is HeliPros, and I'm very proud to be on the HeliPros pilot team. As you notice, my t-shirt is Team HeliPros. I feel very proud to be a part of that brotherhood, and there's some very prominent HeliPros pilots within our club, and they take me under their wing and teach me quite a bit of how to keep this helicopter in the air and increasing my skills. Okay, I want to thank everybody for watching this video, for one, and just to let everybody know I'm very thankful for all the help that I've been given as being a member of the club. If you're interested in getting involved with helicopters, you might consider joining the Triple Creek Radio Control Club and seeking out some of the more knowledgeable pilots here. I'm sure they'll be very glad to help you, because taking on something like a helicopter as such is a complex task. It's very rewarding. It's an exciting hobby to get into, but it does require support. So thanks again for watching, and I hope to see you out at the field. Sideways, well, actually I showed you that. Let's do that part over again. Let's cut that.
Yeah.
Doot. Oh, okay, so, okay. So let's start again. Another cut for gyro stability. Oops. So, cut. Am I on?
Yeah.
So how do we get started again?